In this video lecture, we'll look at series and parallel circuits, how they compare, how they're different, how current and voltage interact within that. So, without further ado, series and parallel circuits. In a series circuit, there's one path for current to flow. So current leaves the battery and it goes through one path. Now, later on, we'll talk about complex circuits where we add multiple things, but for right now, understand that there's one path for current to flow. This means that the current is the same at all points throughout a branch or throughout a circuit. And what the consequence is that the voltage drop across any branch or across any series circuit is going to be equal to the voltage provided by the battery. In a series circuit, the resistors add together. So here we have R1 and R2. The equivalent of R1 and R2 would be the two resistances added together. Now, we also have a voltage drop, so that's some energy used across resistor 1 and resistor 2. That voltage drop, those two combined, is equal to the voltage provided by the battery or power source. So here's just series circuits. When solving problems with circuits, the first step is to reduce the circuit down to the simplest form, and then go back from there and solve for the current, and then reverse back up using the branches. So here we have a 3 ohm and a 6 ohm resistor connected in parallel. This is equivalent to one 9 ohm resistor. This is for series. This is the equivalent resistance of those two. From this, we can use the battery voltage of 12 volts to figure out and determine the current in the circuit. So current is equal to voltage over resistance. So we have 12 volts divided by 9 ohms of resistance. That would give us a current of 4/3 amps. Using that current, we can find the voltage drops across the 3 ohm and the 6 ohm resistor, respectively. That's what I'd like you to do tonight on your problem. For your problem is find the voltage drop across the 6 ohm and the 3 ohm resistor. There'll be another problem later on too, but this would be the first problem. In a parallel circuit, there's many distinct advantages that help us out in our daily lives. The main one is that there are multiple branches, and across each one of those branches is applied the same voltage. So when you have multiple branches connected to a power supply, let's say, for example, our wall power supply of 120 volts, there will be 120 volts of potential across each one of those branches. The way to think about it is when a charge leaves a battery, it needs to get rid of that energy, so it gets some voltage, some joule per coulomb. It needs to use up that energy by the time it gets back to the battery. So that same amount of energy is used in each path. Now, resistors or devices with resistance in parallel add together by fractions. It's kind of the inverse of what we saw before for the series. So it's 1 over the equivalent resistance is equal to 1 over the resistance for the first one, second one plus 1 over the resistance of the second device, etc. Now with current splits at a junction. So the total amount of current entering a junction is equal to the total amount of current leaving a junction. So the amount of current going through each branch is a little bit different, or can be. So here we have a sample idea. We have 2 resistors connected in parallel to some power source. The equivalent resistance is equal to 1 over the first resistor plus 1 over the second resistor, and that's actually equal to 1 over the equivalent resistance. So we have 1/4 plus 1/8, which comes out to equal 3/8, and we take the inverse of that to get our answer. So our equivalent resistance here would be 8/3 or 2.67. So that's how you go through and find equivalent resistance in a parallel circuit. It's important to notice that within a parallel circuit, the 2 resistors actually end up having a resistance smaller than any individual resistor within the circuit. It's this combination of resistors that allow more current to be flowing from the power source. And this is why we have fuses and different devices within our wall to prevent too much current from flowing from the main wire. And actually, we don't even have fuses anymore. We have circuit breakers. But it's whatever the smallest resistor is in parallel has the largest impact in determining the equivalent resistance. A good analogy for this is thinking about a water pump and some pipes. So pipes are generally what we refer to as with a current, so it allows the waters flowing through the pipes, that's current flowing through the wires. The pump provides the energy, how fast the water's moving. The battery provides how much energy each charge has. And within the pipe, so some pipes have smaller resistance or less resistance, or excuse me, more resistance. And so it depends on like the area of the pipe. Now, if you have two pipes that have some value of resistance, their combined resistance is actually less than each individual pipe on its own. So it's kind of the idea of the area. So the smaller pipe has more resistance. So if you have two small pipes, that's equal to like one bigger pipe. So the analogy is more pass within a parallel circuit equals less overall resistance. When a short circuit occurs, this means that the path has very little to no resistance, or almost zero resistance. When you have a short circuit around the battery, you allow charge to flow really quickly. When you have a short circuit within some parallel circuit, it makes that resistance go to zero. So you can kind of bypass a light bulb or some device by adding in a short circuit, because that will make the equivalent resistance of that branch. So here we have the 4 and the 0 and the short circuit on the end. It will make the equivalent resistance 0. The total resistance, once you add this together along with the other resistor here, the 2 ohm resistor, means that the equivalent resistance of this circuit is 2. All right, a couple quick review questions right here. There are more just problems than anything. So, two circuits. Top circuit, calculate the equivalent resistance. Tell me what the current is at each resistor. And then tell me what the voltage drop is across each resistor. The first resistor on the left is a 6 ohm, the second resistor is a 3 ohm, and the battery is a 12-volt battery. For the bottom circuit, please tell me the equivalent resistance. Please tell me the voltage drop across each resistor. And please tell me what the current is in each branch. And then tell me what the total current is from the battery. The top resistor on the bottom circuit is a 4 ohm. The second resistor down is an 8 ohm resistor, and the battery is providing 6 volts of energy. So think about using Ohm's law for this. Go through, definitely show your work on your own sheet within your notebook because it will be helpful. This is basic series and parallel circuits.